We been talking here, chapter 4. We started talking a little bit about the atom. We were talking about sort of experiments that help us understand some of the structure of the atom, and we're leading into some of those. We talked about Dalton's atomic theory last time. Some of the points of Dalton's atomic theory. Again, you should know those different aspects of it. And again, we talked about a couple of parts of it that is still maybe not correct. And the main one was the idea that all atoms of a given element are the same. Again, the existence of isotopes basically mean that that is incorrect. Things like most substances are made up of atoms. Atoms of one element are different than others are okay. Recombination of all of our elements in a chemical reaction, so that's all good stuff. So where we left off was really the structure of the atom. And like I said, we're going to talk about some important experiments along the way. And that helped us understand really the 3 subatomic particles that we find within the atom. So even though an atom obviously is really small, it does have an internal structure. And that internal structure is made up really of 3 particles. And they're what are referred to as subatomic particles, and they are, as you probably are familiar with, our electrons, protons, and our neutrons, with obviously our electrons being negatively charged, our protons being positively charged, and our neutrons, which have basically no charge sort of happening. So we're going to talk about some experiments here that helped us understand some of the nature of electrons, also kind of where all these particles are found within the atom, sort of an earlier thought of where they may be found or how they may be in the atom, and then later on, sort of our understanding of really the modern day version of the atom. So really a lot of work was done in sort of the discovery of different parts and properties of electrons was really started with sort of the development of the cathode ray tube, which is sometimes abbreviated as the CRT tube. And really a cathode ray tube is kind of what is pictured there. They do stream a stream of negatively charged particles. Remember that in chemistry, opposites attract. So negatively charged things would be attracted to positively charged things. And obviously things of the same charge are repelled by each other. They're not attracted to one another. So here in a sort of cathode ray tube, we have sort of an electrical field happening. There's a negative side and a positive side to our cathode ray tube. So the negatively charged particles would move obviously away from the negative side of our tube, heading towards the positive side of our tube. Sometimes they'll put some fluorescent material over here. You can kind of see where it hits and all that kind of stuff. You may be familiar with cathode ray tubes. If you maybe have seen older sort of TVs, have like picture tubes. Those are sort of like cathode ray tubes. Also older computer monitors as well that have like the big backs that kind of come out of it. Obviously not like these, but old CRT type monitors. Those are cathode ray tubes. So what happens in a cathode ray tube is we have these negatively charged sort of particles like electrons are emitted from the cathode and are drawn to the anode plate, which is the negatively charged plate. I'm sorry, the positively charged plate. A hole in the anode allows electrons to pass through. This stream of electrons is what they sort of called a cathode ray early on. As it goes through, like I said, a lot of times they'll kind of coat the surface. So you can kind of see it. It'll fluoresce as the beam sort of hits the surface. And you can really follow the beam of light here. Now, it's important to remember that when we're talking about sort of these subatomic particles, which are positively charged, negatively charged, you can really take advantage of the charge of a particle and the use of a magnet or electrical field to really sort of bend, if you will, the particles. So for example, here, obviously, if we shot a particle from back here and it came through our field and sort of bent up towards the negative side of our electrical field, we would assume that that guy would be a positively charged sort of particle. If we shot a beam and it kind of bent downward towards the positive side of the electrical field, we can make a pretty good assumption that that would be more of a negatively charged one, as it would be attracted. Then obviously if we shot a particle and it really just kind of went straight through with no deflection, we can make the assumption that it is a neutral sort of particle. So a magnetic field sort of works the same way as electrical field. There's kind of north pole, south pole, and we can kind of separate out our particles based on charge. Here's a picture of a cathode ray tube. And again, the electrons would be shooting from here to there. So this would be sort of the positive side. This kind of white covering there is the fluorescence material. And as it would be turned on, you could actually see sort of the beam hit the white part of it. So a lot of work was done with the cathode ray tube, was done by J.J. Thomson. And Thomson did a lot of work with that tube. And what he was able to really sort of figure out as a result of playing with the cathode ray tube was he was able to figure out the charge to mass of an electron. So he was able to figure out the charge to mass of an electron, which happens to be that number there. I kind of went right through, minus 1.76 times 10 to the 8 coulombs per gram. Coulombs is again a unit of electrical charge, so that would be charge to mass, as grams is a unit of mass of an electron. So this was a nice sort of beginning understanding of electrons, these sort of negatively charged particles. The next sort of major experiment that helped us understand a little bit more about electrons was an experiment that was done by a guy named Millikan. And Millikan did what is referred to as the oil drop experiment. And it looks something like what we see here in the picture. We have basically a electrical field sort of set up. He would shoot in his oil droplets here. And obviously they would go through a little opening and they would want to obviously start to drop by natural sort of process there. What he was able to do was he was able to adjust the electrical field in such a fashion. And obviously, as the oil droplets would sort of fall, they would gain sort of a charge. He was able to adjust the electrical field in such a way that basically the oil droplet just sort of hung there. So it wouldn't fall, obviously, or anything like that. And the main result that he was able to determine was the charge on an electron. So Millikan, doing this oil drop experiment, was able to determine the charge of an electron, taking that with what Thomson was able to figure out, which was the charge to mass of an electron. And Millikan was able to figure out the charge of an electron. You get rid of those two. Taking kind of both of those experiments together, the mass of an electron was able to be sort of determined. And if we look at the mass of an electron, it ends up being something like 9.09 times 10 to the minus 28 grams. That is a very small number, right? It says minus 28 means heads like 28 places to the left, right? And put a bunch of zeros in front of it. So it's going to make it a really small number. So the first two things that you should be aware of is obviously the use of the cathode ray tube was used by Thomson to figure out the charge to mass of an electron, followed up by the oil drop experiment. And from the oil drop experiment, it's able to figure out the charge of an electron. Again, kind of putting those experiments together, the mass of an electron was able to be determined. Any questions on that there? Okay. So let's talk a little bit about the proton and the nucleus. So by the early 1900s, two things were really thought of about the atom. Obviously, from our experiments here with our cathode ray tube, they contain these negatively charged electrons, and they were also believed to be electrically neutral. So if it was clear that the atom contained negatively charged electrons, there had to be something of a positive nature there as well to balance out, obviously, all the negatively charged electrons. So around the turn of the last century there, the accepted model was actually the one proposed by Thomson. And that model, the atom, was one that is sometimes referred to as the plum pudding model. And that's sort of like an English dessert, right? Some pudding, some raisins, and stuff like that. And basically what he said was that the atom itself was really the sphere of positive charge. So you have all this positive charge sort of spread out over the sphere. And he thought that embedded inside the sphere of positive charge were these negatively charged electrons. And one of the main sort of features of the plum pudding model was also the idea that they believed that most of the mass of the atom was actually made up of these electrons. So they felt that most of the mass of the atom was these electrons. So this is really sort of the accepted model of the atom. This one that was proposed by Thomson. We got this positive charge that's really sort of spread out all over the sphere. Electrons sort of embedded in there, kind of like the raisins in the dessert. And again, most of the mass of the atom, they're making up of these negatively charged electrons. So this was really sort of a model that people believed atoms were, until really the next major sort of step along the way that helped us better understand the atom. And this was really the experiment known as the gold foil experiment. And the gold foil experiment was one that was done by Rutherford and others. And basically what they did was they took pieces of gold foil and other metals, and they shot alpha particles at them. And what alpha particles are radioactive, positively charged particles. They're essentially the helium nucleus is basically what they are. By the way, there are beta particles that have been used in these sort of experiments, not necessarily the gold foil experiment, but just in experiments in general. These are negatively charged radioactive particles. And there's also gamma rays that are sometimes reused along the way here in some of these experiments. Once again, not particularly in the gold foil experiment. Gamma rays are kind of neutrally charged radioactive rays. So you can almost equate these sort of three radioactive particles, which were very commonly used in these sort of experiments to understand the atom. They sort of relate to the three subatomic particles. You know, alpha particles are positively charged particles like protons. Beta particles are negatively charged particles like electrons, and gamma rays are kind of like neutrons. They have no charge associated with it. But here with our alpha particles, our Rutherford's experiment, he did use the alpha particles as the ones for the experiment. And what he thought would happen and sort of what he observed happen were sort of two different things. So if we kind of go back to the plum pudding model, what he thought would happen was as he shot these positively charged sort of particles coming through basically this sea of positive charge, because they're positively charged, because they're moving really fast, they would be expected to sort of go through and kind of pop through, but there would be some deflection that would occur because it's basically something that's positive and positive that's happening. But because they're moving pretty fast, it would be able to kind of punch through. Kind of like if you took like a big piece of paper or a piece of paper and that was like all your positive charge, and somebody held one side of the paper and somebody else held the other side of the paper, and you shot like a pin at it, right? You would expect the pin moving really fast to be able to punch through, but there'd be a little bit of deflection as it sort of popped through the paper. And that's sort of what they envision would happen here based on the model of the atom that was the Plum Pudding model. What they actually saw was something quite different. What they actually saw here, and here's sort of a setup of Rutherford's experiment. We have a source of our alpha particles over here. It's shooting at really our gold foil here, which are atoms basically. And the little screen there is sort of a detection screen. And what they saw for the most part when they did this experiment was that as they shot these particles, most of them had no problem, just kind of sailed, pretty much right through with no problem, no deflection, just kind of went on its way right across. But what they also observed, which was kind of surprising to them, was every so often when they would shoot these particles, they would see some particles kind of bounce off at these really sort of large angles. And occasionally it would kind of shoot back, at the sort of source. And that was sort of unexpected. Again, they felt that in most cases, they would see all the particles which are positively charged sort of pass through and have some deflection. So they found, as I mentioned, that most of them went through undeflected. But every so often they did see these alpha particles scattered at these really, really large angles. Now, they compared it to kind of shooting a gun at a piece of paper and having basically the bullet come back to you. So it was kind of surprising to really see those heavy sort of alpha particles, which are moving really fast, being able to be reflected at these really, really large angles. So if we think about sort of what they found, we could think about what happened. First off, the ones that went through pretty much undeflected, no problem. What did they hit? They most likely hit nothing, right? So like if I threw a pen or a ball or something straight across and it just goes straight across, doesn't move any which way, right? It obviously, nothing was in its pathway. But in order to make those alpha particles, which are really, like I said, kind of heavy, really positively charged and moving really fast, to bounce off at really, really large angles, they had to hit something that was very, what type of charge? Yeah, they had to hit something that was very, very densely positively charged to basically make those alpha particles bounce off at those really large angles. And what they had to think about was our original sort of thought of the positive charge in an atom is it's like spread out all over, kind of moved all over. So what would that mean is instead of the positive charge really being spread all over the atom, the positive charge really has to be sort of centrally located. So if you take my sort of paper example, instead of having a big paper that's not folded, but if you take the paper and you fold it and keep folding it, and now like your positive charge folded paper is like this big. If you try to throw a pen through it, it is going to definitely bounce off because all of the positive charge are basically concealed in one area. So what they came up with was obviously what we see here. We see that what they saw is those guys going through pretty much no problem. But again, that kind of really dense positive core in the middle. So they had to basically do a couple of things. And first thing was pretty much say that the sort of early model here, our Thomson's Plum Pudding model of the atom, is really no good. So they had to kind of take that early idea of positive charge spread out with our electrons embedded and go not so good. And they basically came up with this idea that the atom is mostly empty space. And again, that makes sense based on the electrons being able to kind of fly through undeflected. They really didn't come in contact with anything. They came through that empty space. It has a very dense positive core, which they called a nucleus. And as we will later find out and can imagine, that is where we have our protons basically housed, which are positively charged, which makes sense based on the really large deflection that we see. Later on in like the 1930s, neutrons were discovered to also be in there in the 1930s with no charge, obviously not at this particular point in time. And the idea here was that the electrons were out from the nucleus at some distance, and the electrons are sort of traveling in that empty space. So our electrons are traveling in the empty space. And as we talked about, or we will talk about once again, electrons do travel in a random sort of pattern. Again, they don't travel in a nice kind of pretty circle type pattern or anything like that. Is there an attraction between the electrons which are flying around and the nucleus? And the answer is yes, because the nucleus is positively charged. The electrons are negatively charged. So although they are flying around in sort of that empty space, there's an attraction between the electrons and the nucleus, which sort of holds them there as well. And then the last major sort of difference between the Plum Pudding model and Rutherford's sort of modern model is most of the mass of the atom is the nucleus. So the nucleus is pretty much where most of the mass of the atom resides. And as I mentioned there, later found obviously protons along with neutrons being found inside the nucleus. So you do need to know Rutherford's experiment, sort of what it was, what happened, what they expected to happen versus what they actually saw happen. And obviously you did need to know sort of moving away from the Plum Pudding model of the atom to really our modern version here of the atom. Any questions on that there? Yeah. Yeah, so once again, what they thought would happen is pretty much in this picture here. So what they thought would happen is, again, all this blue is basically positive charge, right? And then they were shooting these positively charged alpha particles at it. So what they expected was, because the alpha particles are moving really, really fast and they're relatively heavy-ish, what they thought would happen, because all the positive charges really spread out, kind of diffused over the entire sphere, was it was kind of would be able to pop through, but there would be some deflection as it went through. So kind of like my example, if you kind of held that piece of paper up and you kind of poke the pin through, right? You'd be able to poke the pin through, but it'd be a little bit deflected, right, as it kind of pops through. And that's ultimately what they sort of thought would happen, is as it would be moving through the sort of positive jello there, it would kind of bounce a little bit and be a little bit deflected. What they actually saw was that most of them just went through pretty much no problem. It didn't really go one way or the other, kind of went straight through. And that again led us to the idea that, you know, that positive charge is not really spread out all over, but it's probably mostly empty space. But it definitely does have positive charge that's very, very concentrated in the nucleus. And that accounted for what they saw here, that you know, every so often these guys would bounce off at these really large angles. Other questions? So this is a table of some of the experiments we talked about that helped us sort of understand, you know, the atom and different parts of the atom, the electrons, protons, and stuff. So it's sort of a summary table of those experiments that we talked about. The gas discharge tubes is sort of the forerunner to the cathode ray tube, but those are pretty much the main results that came out of it. Now let's talk a little bit about the protons. So obviously, through Rutherford's experiment and such, it was found that that positively charged particle was concentrated in that nucleus. And through experiments, it was found that the mass of a proton is 1.67252 times 10 to the minus 24. If you remember, the electron was something like 9.09 times 10 to the minus 28 grams was the electron. So you can see minus 24 is a much larger number than minus 28. In case you're not sure, when you have a negative exponent, the smaller negative exponent is the larger number, because minus 24 means only 24 places to the left. Minus 28 means 28 places to the left with a lot of zeros. So The proton is about 1,840 times heavier than any electron that's flying around. And that also helps us understand sort of what Rutherford said, that most of the mass of the atom is the nucleus, because in the nucleus is our protons, which are each 1,800 so times heavier than any electron flying around. So that also fits very nicely with the idea of Rutherford that most of the mass of the atom is actually the nucleus, where we do find those particles. So at this stage, sort of the investigation of the atom, the nucleus, like I said, comprises most of the mass of the atom, but it has about 1 over 10 to the 13th the volume of the atom. So you could think of like the nucleus as, like something on the 50-yard line in a football stadium, and sort of the entire football stadium as, kind of the rest of the atom and stuff like that. So it's relatively small, but obviously contains a lot of the mass of the atom because it has those protons, and again later on obviously has the neutrons that are there as well. So let's talk a little bit about neutrons. It really wasn't until about 1932 that some experiments done by a guy named Chadwick really sort of recognized the existence of that third subatomic particle, which is the neutrons. He did a lot of work with beryllium and alpha particles, and what he saw was that they would sort of emit this really sort of high levels of energy radiation that really resembled our gamma rays. And if you remember, our gamma rays are really kind of no charge, pure energy radioactive sort of particles or rays. So he kind of witnessed something sort of coming off that was very, very similar to our gamma rays. And later experiments showed that it had a mass, these neutrons, of 1.67495 times 10 to the minus 24 grams. Now you may be wondering, why do they take it so far out? And it's because of what we see here, that it is 1.67252. So 1.67252 times 10 to the minus 24 grams are our protons. So they are very, very close to one another in terms of their mass, but it is actually the neutron that is the most heaviest, just barely coming out to about here, takes them out. But once again, in comparison to our electron, which is 909 times 10 to the minus 28, we could also see here that neutrons are also about 1,800 or so times heavier than an electron. So this also makes sense when we think about where we find these particles. We find the protons and neutrons in the nucleus of an atom. So that again makes sense that most of the mass of the atom is made up of the nucleus, because it contains protons and neutrons, which are both individually 1,800 or so times heavier than any electron that's flying around. So again, that all fits very well based on what came out of sort of Rutherford's experiment. Any questions on that? So again, both of these guys are in the nucleus, and obviously electrons are out from the nucleus flying around. Any questions on that there? So once again, our masses of each of these guys, you should be familiar with the masses. You definitely should be familiar with which one is the heaviest, which would be the neutron, followed by the proton, and then obviously the electron being the lightest. I would say the electron mass sometimes comes up in your future sort of chemistry classes and stuff like that. So, they might ask you what that number is along the way. So this is sort of an idea of the atom here, of what's going on. Here we see our very small sort of spot here, which is our nucleus, where we have our protons and our neutrons basically housed. This sort of reddish spot here is basically what is sometimes referred to as sort of that empty space, or the electron cloud. And that basically is where the electrons are flying around. That is sort of the empty space, if you will, as to where the electrons are basically flying around in, again, in a pretty random pattern about the nucleus. They are going to feel some attraction, obviously, to the positively charged nucleus. As we go through it there. All right. Now, yes, sir.
Just a little information, and I also found out that if you add the mass of a proton and electron together, it equals the mass of a neutron.
Perfect. I like it. Thank you. So most of the chemistry of an atom comes from an electron. They are involved basically in bonding, and it does make sense if you think about electrons, which are obviously on the outside of the atom. So when two atoms come together, like this fly, when two atoms come together, it's going to be the electrons, which obviously are going to come in contact with each other. Now, they are the ones that are involved in bonding, depending on how close they are to the nucleus, is why only certain electrons actually do participate in things like bonding and chemical reactions. And those, as we'll talk about, are really the valence electrons, which are the outermost electrons, sort of furthest away from the positively charged nucleus. So that brings us to a couple important things. The first one is an atomic number, mass number, and isotopes. Let's talk a little bit about each of these. So first off, the atomic number, which is abbreviated with a Z, that is the number of protons there are in the nucleus of an atom. Now, if we are dealing with something that is neutral, and as we just talked about, basically, there are protons which are positively charged, electrons which are negatively charged, and neutrons that have no charge. That means that if it is neutral, the number of protons should equal the number of electrons if it is a neutral. So the atomic number will also tell you that information. It's important to note, though, that if you're asked just a straight up question of what is the definition of atomic number, it is only the protons. So it is only the protons is the actual definition. But if it is neutral, it will also tell you the number of electrons. So for example, if we go 7 is nitrogen's atomic number, which means a neutral nitrogen atom has 7 protons, would also have 7 electrons. We can find the atomic number up there on the periodic table. And it is the number that we see above the symbol. So when we look at the periodic table, all the numbers that come above the symbol are the atomic numbers. One thing that you will notice if you look at the periodic table there, that's, for example, hanging on the wall, there is no number that's on top of the symbol that repeats. So every single element has its own atomic number. That means that the particle important in terms of determining what element you are dealing with is the protons. So it is the protons that basically tell you what element you are dealing with. And that means that you will never, ever find a fluorine atom with an atomic number of 7, because atomic number 7 actually should be the atomic number 9 and protons. So it is the protons which are the most important in determining what element you are dealing with. Another really important number is the mass number. And the mass number is sometimes abbreviated as an A. And the mass number is the total number of protons and neutrons that there are in an atom. So mass number, number of protons and neutrons, atomic number, number of protons. The importance of those two numbers are, if we take our mass number, which is the number of protons plus the number of neutrons, and we take our atomic number, which is the number of protons, and we subtract them, that will give us the number of neutrons. So the way that you could figure out the number of neutrons there are is to take the mass number minus the atomic number, and that will give you your number of neutrons. Now, all three of those things, when you're asked to sort of calculate the atomic number, the mass number, how many protons, electrons, or neutrons you have, those all should be positive whole numbers. So that brings us to the periodic table, and we know that this is the atomic number. And underneath on the bottom there is a number. Is this number the mass number? The answer is no. So the mass number is not found on the periodic table. If you look at all the numbers that come underneath the symbols, for the most part, none of them are whole numbers. They're pretty much all decimal numbers. So you should be able to calculate the mass number based on the information given to you in the problem. The number on the bottom there is the atomic mass. So that is actually the atomic mass of the element, not the mass number. What oftentimes confuses people is very simply, a lot of times the mass number and the number you see on the periodic table, they're very close to like being the same number, because frankly, they're based off of like protons, electrons, and neutrons. So only the atomic number can be found on the periodic table. The mass number you got to calculate based on the information given to you in the problem and not get it from the periodic table. So if you find yourself on the test being the person writing those numbers that have decimals for mass number, you know, just lay yourself up an X first. Yes, save me the trouble. So isotopes are important things as well. And as we talked about, isotopes are really one of the things that make part of Dalton's atomic theory incorrect. What isotopes are the same element, but they have different masses. So as we just talked about, the particles that are really important for something to be a particular element are the protons. So when we have isotopes, they would definitely have the same number of protons because they're the same element. They will also have obviously the same atomic number because of that. So what gives them different masses is they have different numbers of neutrons. So isotopes are guys that are the same element, but they have different numbers of neutrons. So for example, here, all elements will have protons, electrons, and neutrons, except for hydrogen. So hydrogen only has a proton and an electron. It does not have a neutron, but all other elements will have all three of those particles, except for, again, hydrogen, one proton, one neutron, I'm sorry, one proton, one electron, no neutrons for hydrogen. Now, if we look at hydrogen, hydrogen has one proton and no neutrons. Deuterium, which is kind of like heavy hydrogen, has one proton and one neutron. And tritium, which is actually the radioactive version of hydrogen, has one proton and two neutrons. One very common way that we write sort of the symbols for isotopes is what we see on the bottom here. We use the symbol. On the top left, we put the mass number. On the bottom left, we put the atomic number there. So if we were to do our isotopes here for all three of these guys, we would start with hydrogen. And if we were not sure what hydrogen symbol was, because it has one proton, it would be number 1 on the periodic table. And that would tell us that it is hydrogen. And since it has one proton, bottom left would be the atomic number. 1 plus 0 is 1 for the mass number, which would go up on top. And that would be the proper symbol for hydrogen with the mass number and atomic number. Now, if we did it for deuterium, even though it doesn't say hydrogen, we would know it's hydrogen because it has one proton. So once again, we would go to the periodic table and see number 1 is still hydrogen. And we would put our atomic number there. Our 1 plus 1 here is 2, which would be our mass number up on top. And lastly, tritium, which again doesn't scream hydrogen to you, but when you see it has one proton, once again, that would tell you the atomic number is 1, and the symbol would be hydrogen. And here, obviously, 1 plus 2 would give us 3 for our mass number. So basically, when we write our symbols like this, You take the top number minus the bottom number, gives you the number of neutrons. So 1 minus 1 gives you 0 in the first case. 2 minus 1 gives you 1, and 3 minus 1. So you take kind of the top number minus the bottom number, gives you the number of neutrons, right? And you obviously the top number being the mass number, bottom number being the atomic number. So that's a very common way that we do write sort of these symbols. Another way that you sometimes will see symbols written, for example, like this, copper 64, the dash here with the number, it's actually just the number is the important part. That number is actually the mass number. So I know that's the mass number because if I go to the periodic table, the number above copper is 29, which would be its atomic number. And if we were to write it like our formula here, it'd be 64 up on top and 29 on the bottom. In this case, the number of neutrons would be 64 minus 29, which feels like 35, hopefully. Would be the right answer there. Any questions on that there? Any questions on atomic number, mass number, and those type of things? All right, I think it's a good place to lay up.